The second PowerPoint for our statistics unit is on correlation of two variables. So we're going to learn about correlation, what a contingency table is, and what a scatter plot is. In our last PowerPoint, we just used one variable, and it was salmon length. We saw female salmon length and we saw male salmon length, but in the end it was just one variable, the length of salmon. In this PowerPoint, we will now work with distribution that deal with information about two variables. So we could talk about the length of salmon and the age of a salmon. Those are two variables. Working with two variables shows us certain relations between the variables. For example, is there any relation between the length of a salmon and its age? Well, yeah, of course. The older a salmon is, the bigger and longer it will get. So there is a relation between the salmon and its age. And we'll talk more about this relationship. Let's define the word correlation. Split it up first. Co-relation. It's the relation between two values in a distribution, whether there is one or not. It's possible to describe the type of relation, the direction of this relation, and how intense this correlation is between two variables, like, for example, our age and height. We could say, how intense is it? What kind of correlation is it? Also, marriage and gender is another example, but there are many others. A correlation can be positive when one variable increases or decreases and the other variable also increases or decreases. So if both variables increase or both variables decrease, it's said to be positive. If one variable increases while the other decreases, or vice versa, the correlation will be negative. Right now, this is not as easy to picture, but when we talk about other things in this PowerPoint, it will start to make more sense to you. So we have a positive correlation, we have negative correlations, but a correlation can also be a zero correlation, like there's no relation between the two variables. It can be a weak correlation, moderate, strong, or perfect, depending on the results of its values. We will see examples of this when we work with scatter plots, which are coming right up. A contingency table. Well, first, stem and leaf plots were used when talking about information about only one thing. So we're talking about one variable, length of a salmon, we'll use stem and leaf. Whenever you're talking about one variable, just use a stem and leaf. But in this case, we're using two variables. So a contingency table is used to visually see the relation between two variables. So let's just see an example of what a contingency table is. Here's a contingency table that we're going to look at that represents the age and number of branches of 18 trees of the same species. So here are 18 trees of the same species. And here is what is our contingency table. Now, it might be overwhelming at first, but don't worry. Here are our points. Our x's represent the age, and our y's represent the number of branches of these 18 trees. So here's what we do. We look at each point, and we tally under which box they go in. So here, 12 years old, 160 branches. It's going to go in this box here, right? Because it's between 10 and 15 years old, and it's between 100 and 200 branches. So we'll have one here. This one is 13 years old, and it has 145 branches. It'll also go here. This one is 13 years old, but it has 220 branches, so it's going to go in this box here. And you would do that for every single one of those points. And then you would tally together how many each box has. And it's possible that some boxes have none, because there are no tree between 15 to 20 years old that has between 100 and 200 branches. That's fine, okay? But in the end, you would just basically get rid of all of the ones that you do and plot them onto your contingency table. And in the end, you'll have something that looks like this. And what's important is that you remember to total at the bottom here. Each column totals and each row totals. And when that happens, you'll have the same total that we have here, 18 trees here. So we'll know the total of trees, but we also know the total of branches between 100 and 200. We'll know the number of branches the number of trees between 200 and 300 branches, and so on. And you can tell a lot just by looking at this table. And we'll get to that in a second, but what's important is that you understand how it is that I plotted my points. It's up to you how you decide to divide your intervals. I decided to divide my branches intervals by 100 just by looking at the big numbers, and I decided to change or to put my intervals for years, for ages, between like 5 intervals, because the numbers were so small. That's completely up to you, though. There is no right or wrong answer as long as you're consistent and you pick the same intervals for the branches and the same intervals for the age. What is it specifically, this contingency table? So let's look at some details of this contingency table. Some I've already talked about, but we'll go over anyway. One of the variables associated with the first column and the other variable is associated with the first row. So we have number of branches and then we have age, two variables, one in the columns and one in the rows. The data values can be grouped into classes. We call these classes, these intervals here, classes. The row and column totals indicate the frequencies of each of the values or classes. So here we know that there are 2 in the class of 100 and 200 branches, and we know that there's 3 in the class of 10 to 15 years, and so on. The lower right cell down here contains the total number of data points in the distribution. So this here will tally all of these and all of these, but it has to be equal to the total number of data points in distribution. A correlation, so the relation between two variables, is said to be linear when the majority of their occurrences follow one of the two diagonals. So here we have two diagonals in this chart. Does this one follow the diagonal? Yes, it does, because you'll see that most of these data points are in the diagonal. So we could say that there is definitely a linear correlation in our contingency table. Now, you're going to have to know how to make one. So here's our contingency table. I just want to note two important things. The square brackets. You've seen these before when we were doing step functions. Remember, it's 10 to 15, not including 15, and then I include the 15 in my next interval. Here, same for 200. And you will always have these intervals, these brackets, when you're working with contingency tables and putting your values into what they call as classes. You choose how you group your classes based on the values that you're given. Now, we had a large number for branches and we had a smaller number for age. So for me, it made sense to put my branches into classes of 100 and my ages in classes of 5. If it's easier to go up by 5, go up by 5. If the numbers are big and you think it's better to go up by 100, you go up by 100. That's completely based on the data values that you were given. Now let's analyze this contingency table, because just by looking at it, there's a lot that we can tell from this contingency table by our totals and by our classes. The first thing that we could say is 6 out of 18 of the trees in the sample are 25 years or older. So here's our 25 years. The total for 25 years or older is 6 plus 0, which is 6. And the total number of trees in the sample are 18. So 6 out of 18 of the trees in the sample are 25 years or older. We can also say that 80% of the trees containing 300 to 400 branches here, 300 to 400 branches, are less than 25 years old. So there are 4 trees in this class that are less than 25 years old, and there are a total of 5 trees in this class. So 4 out of 5, or 80% of the trees in this containing this many branches are less than 25 years old. And just another example, 45% of the trees have between 200 and 400 branches. So here's the 200 to 300 total plus the 300, 400 total, and that's 4 plus 5, which is 9 out of 18. So it's 45% of the trees that have between 200 and 400 branches. This is just an example of something that we can see when we're analyzing a contingency table. But there are a lot more that we could say just by looking at this table. Now, let's graph this contingency table. Graphing this contingency table will look something like this, where we have our age down here. So all I have is I redrew my intervals down here, and I redrew my intervals for branches up here. And then I said, okay, was there a tree that was 10 to 15 years old and 100 and 200 branches? Yes, so I just dot a point. Now, even though there's like 3 in this, it doesn't matter, you only dot 1 point. And you just dot points where there are values in the boxes. So if we go back to our scatter plot here, even though in our first box there are 2 trees, we just put 1 dot here, okay, just to say that there is something there. And then we continue by plotting them here. just single dots where information can be found from the contingency table. The straighter the scatter plot, the more linear it is. And there's a lot that we can see from the scatter plot that we're going to talk about later in terms of describing its correlation. Let's analyze the scatter plot. So one of the variables it's not important which one you pick, but one of the variables here is associated with the x-axis. In our case, it was age, and one of them is associated with the y-axis. And in our case, I put the branches now, but it doesn't matter which one you put where. You'll still get the same plotted points. Each of the ordered pairs in the distribution is represented by 1 point. Even if there are more than one data for the variables, it's just 1 point. Okay, even though there were 3 trees in this box, we only put 1 dot, 10 to 15 years old, 200 and 300 branches. A correlation is linear when the points form a somewhat straight line. So in this case, they're kind of straight, right? They're kind of in a diagonal. We could say that they're almost linear. A zero correlation is when all the points are just randomly distributed in the plane. So if you have points like over here and they're not really setting anything up, it's a zero correlation, meaning there is no relation between the two variables. Correlations are negative when the points start up top here and then work their way down. But that's not the case for ours, because ours are from the bottom up, so it's a positive correlation. The following images will describe the different characteristics of linear correlations, and this is where scatter plots get important. You need to know that correlations can be positive or negative, or they can be strong, they could be weak, they could be moderate, they could be zero, or they could be perfect. Here are some examples of negative correlations. Now remember, starting from the top and then making their way down to the bottom, you have a negative correlation, and all of these points are everywhere. There's not really any kind of cohesive pattern to them, so it's a weak correlation. Again, negative correlation starting from the top and going to the bottom. These points are a little bit more cohesive than these points, so we'll say that they're moderate. Now you'll notice that the points in this plot are a lot closer together than the other two that we've seen. So we can say that it's a negative strong correlation. Finally, if all the dots form a perfectly straight line just like this is a perfect negative correlation. The positive correlations are basically the same thing, except instead of starting from the top and going from the bottom, they start from the bottom and they go to the top. So this is a weak correlation because the points are pretty much scattered everywhere, but it's positive because it starts from the bottom and makes its way to the top. This is a more moderate correlation because, as you see, compared to these two, the points are closer together and they're forming some kind of cohesiveness. So this is a moderate positive correlation. But in this one, the points are closer, even closer together. So we'll say this is a strong positive correlation. And finally, this is a perfect positive correlation, starting from the bottom going to the top, all the lines in a perfect straight line. Zero correlation is when you can't even tell if it's positive or negative because the points are kind of in a square. So you can't tell if they're starting from the bottom going to the top or starting from the top and going to the bottom, and they're all scattered everywhere, so you can't tell. This means that there is absolutely no relation between the variables, the two variables, in this case. Try it yourself. Here's a table representing the heights of 20-year-old men in France over the years. So here are the years, and here are the height in centimeters. Try and make your own contingency table with this information and plot that information on a scatter plot. Your answers will depend on how you decided to split your intervals, but this is how I decided to do it. So I split my heights here in 5s, and I split my years in 10s. Okay, and when I plot everything down, I noticed that there were 2 instances between 1880 and 1900 where the height was between 165 and 170. I noticed that there was no height between 165 and 170 after 1900. Then I noticed that between 1900 and 1920 there were 2 people who had between 170 and 175 centimeters in height. But there were 3 people from 1920 to 1940 who had between 170 and 175 in height. And again, I just continued going and I plotted everything into my contingency table and I totaled all my columns and all my rows. And I get the same amount that I had in the contingency table and in the chart that I gave you, 9 data values. Okay? And again, there's a lot that you can tell from looking at this. I could say, okay, well, 2 out of 9 of the men are between 175 and 180 centimeters. I could say that 2 out of 9 people have height between 165 and 170 centimeters between these 2 years, and so on. These are things that you should notice in your contingency table. Now that you have all of your contingency table plotted, you have to put these into a scatter plot. So first, pick one to be your x and pick one to be your y, and then plot these intervals onto the plane. Then you're going to put a dot where you see that there are data values here. And by looking at it, it's pretty much forming a diagonal, so I'm assuming that my points are going to look linear. And I'll be correct because, as you see here, after plotting my points, I had at least one between 1880 and 1900 that was 165 to 170 centimeters. I actually had 2, but I only needed to put 1 dot. And you'll notice that it makes a straight line. So this is a linear, positive, and we could say it's pretty strong. It's a strong correlation. So this is the end of your section on correlation, contingency tables, and scatter plots. Our last new thing that we're going to learn in stats is the correlation coefficient and regression lines.